Welcome and thank you for joining. We'll take a look at some homework questions from page 106, number 13. As you can see in all these questions, we have to use the chain rule in Leibniz notation to find dy dx at the given value of x. So as you can see here, we are given the equations of y in terms of u, and then the equation of u in terms of x, and we need to determine dy dx at the indicated x values. Now, before we get started, I want us to take a look at a simpler example so that we understand the Leibniz notation formula for the chain rule and learn how to use it in the meantime. So I'm going to bring in here a simpler function, y equals u to the power of 1 over 2, and where u is equal to x squared plus 3. So we say that in Leibniz notation, if we want to find dy dx, we use the formula dy dx equals, we differentiate y in terms of u first because that's a relationship we have between y and its independent variable. And then we differentiate u in terms of x and multiply them. But how does this formula work and where did this formula come from? There are different ways to proving this, but I want to prove this to you through a simple example because in mathematics, some formulas have been, analyzed and created and based on observations, and some formulas based on proofs. And this is one of the formulas that is easily understood when being observed in a simpler setting. So here we go. If we have the function y equals u to the power 1 over 2, where u is a function that depends on x, it means that we have a composition of function y, where the outside is the square root function. So in other words, we're going to say that to differentiate the function y in terms of x, we will need to express y in terms of x. So instead of u, then we're going to write x squared plus 3 and then to the power of 1 over 2. So this would be our u function to the power of 1 over 2. So as you can see, we have the outside function here, the power of 1 over 2, and the inside function, which is x squared plus 3. So what we are going to do is differentiate it by using the chain rule. So we'll say that dy dx equals, we have the outside function, which is a power of 1 over 2. Just use the power rule for it. 1 over 2 minus 1. The expression inside it won't change, so x squared plus 3. And then we have to multiply by the derivative of the inside, which is the derivative of x squared plus 3. Now, as you can see, this differentiation here is very straightforward. We call this the explicit differentiation. So we can simply differentiate this by using the power rule. And we will also be differentiating this outside function, so which I would write in a simpler form as 1 over 2. 1 over 2 minus half, that would be negative 1 over 2. And then we have u in here, as you can see. So I'm going to bring u in, and then in here we'll have the derivative of the function u. So x squared plus 3 represents u, so we are writing the function u itself. So as you can see here, we have created the du dx. And what we do see in here is simply the derivative of y in terms of u. So we can rewrite this as dy du. And this will multiply, here we go. Let's go be consistent with our colors here. So du dx. So this is how the Leibniz notation or differentiation in Leibniz notation works. So basically in Leibniz notation, we differentiate the outside function in terms of whatever function we you input inside y, and then you multiply by the derivative of the inside, which is the du dx. And I think that now we're ready to start off with our examples. So we are going to use this formula in a straightforward way. We're going to use the equations of y to differentiate in terms of u and multiply by du dx. But at least now we know and we understand where this formula comes from. So I'm going to start off with number 13a. So let me just copy this entire thing, I guess, because otherwise it doesn't work in here. So let me see if I wanted to actually paste only one of the equations, but because it is copy after copy, it doesn't allow me to. It's okay. We're just going to write the equation a. So we have y equals 3u squared minus 5u plus 2. And we have function u equals x squared minus 1. We're finding the derivative and evaluate at the end at x equals 2. I don't want to substitute x by 2 right now because very often people make the mistake of substituting directly and then they mess up the solution. So let's find the derivative in the most simplified form. We'll say that this would be dy du, and that's because we can only differentiate y in terms of u because that's its independent variable. But because u is a function on its own, then we have to differentiate the function u, which is the inside function of y. So let's substitute now. We have du of 3u squared minus 5u plus 2. You see now we have explicit differentiation. So we have direct relationship between the variable in the function and the variable in the derivative. And this will be multiplied by d dx of function u, which is x squared minus 1. Continue simplifying or finding the derivative finally. So 3 times 2 is 6, u minus 5. That would be the derivative in terms of u. And then the derivative of the inside will be 2x. So remember that we're trying to find dy dx, which means that in the differentiated function, we need to see only x, which means that u has got to go. And we'll replace u, guess with what? With x squared minus 1, because u is equal to x squared minus 1. And then minus 5, and then times 2x. Simplify some more, why not? We have 6x squared minus 6 minus 5 multiplied by 2x. So we'll say that dy dx would equal, I'm going to bring 2x to the front since it is a monomial, and then 6x squared minus 11. So if we want to evaluate this derivative at x equals, let me double check again at what x values, x equals 2. Then we'll say that that would equal 2 times 2, and then multiplied by 6 times 2 squared, and then minus 11. So that would be 4. And 6 times 4 is 24 minus 11. Obviously, you can do this super fast in the calculator. And then we got 24 minus 11, 13. And 13 times 4 is equal to 52. And that would be dy dx measured at x equals 2. So in a similar way, you can do the next question and the question after that. As you can see here, this is kind of easy, so very similar to what we did before. It does have a more complicated inside function. You know what? Let's try this as well. So here is my new method of copying the questions down. So we have the function y equals, let's open up a new page. We'll just copy and paste the entire thing. So we're doing question B this time. So we have function y equals 2u cubed plus 3u squared. Function u is x plus x to the power 1 over 2. We're evaluating this at x equals 1. So let's get started. dy dx equals dy du times du dx. So ddu, or the derivative in terms of u of function y, is the derivative in terms of u of 2u cubed plus 3u squared, multiplied by the derivative of u in terms of x is ddx of x plus x to the power of 1 over 2. Start differentiating now. We have the power rule, that's 6u squared plus 6u. Now multiplying derivative of x, which is 1, plus 1/2 of x to the power of, remember, 1 over 2 minus 1, which is negative 1 over 2. We do this so often, so you can do that in your head very fast. And now we have to express dy dx in terms of x. So a little bit of algebra involved in here. So we'll have 6. The value of x, the value of u in terms of x is x plus x to the power of 1 over 2. This will be squared. And then plus 6, x plus x to the power of 1 over 2. Close the brackets. And then we have 1 plus 1 over 2, x to the power of negative 1 over 2. So now we have the derivative in terms of x. And obviously it's in unsimplified form, so you can take out 6 if you wish. But because we're only asked to evaluate the derivative, we can save that step and then simply substitute x by 1. So we'll say that at x equals 1, dy dx would equal, open up brackets, we have 6, we have number 1 wherever we see x, and then to the power of 2 plus 6, and now we have 1 again, plus 1 to the power of 1 over 2, and then we have again 1 plus 1 over 2, number 1, this time to the power of negative half. So simplify, we have 6 times, here we go, 1 to the power of 1/2 is 1, so together 2. So that makes it 2 squared, plus 6 times, again, times 2. And then we have 1 plus 1/2, and 1 of 1 to any power also is 1, so times 1. So we have 6 times 4, 24 plus 12, multiplied by 1 plus 1 over 2 is 1.5, or 3 over 2. 24 plus 12, that will make a 36. 36 over 2 is 18, and 18 times 3 is equal to 54. So we're going to say that would be the value of dy dx measured exactly at x equals 1. So let's move on to the next example, example C, or question C. So let's do question C down here. We have function y equals u squared plus 3 to the power of 3. Function u is x plus 3 to the power of 2. We're evaluating it at x equals negative 2. So as you can see here, we're dealing with some chains as well as product rule. So nothing to worry, just a longer process. We'll write out the formula. Dy dx is dy du times du dx. So that means we have d du of function u squared plus 3 to the power of 3. And then we have multiplied by d dx of function u, which is x plus 3 to the power of 2. So let's start differentiating. Now notice that here we have product rule. So we are going to use the product rule to differentiate this function, which means that we are differentiating the first factor, the factor u, the derivative of it is 1, and multiply it by the other factor, which is u squared plus 3 to the power of 3. And because it's product rule, we're adding now the derivative of u squared plus 3 to the power of 3. Now notice that here you have an outside function, a power of 3, which would differentiate to 3, whatever is inside the brackets, u squared plus 3, 1 power less than 3, that is a 2. And then you have to multiply by derivative of u squared, which is 2u. Now, what we got in here was just the derivative of this factor. We still have to multiply by the other factor, which is u. And that will make the derivative of function y in terms of u. The derivative of u in terms of x will have, again, an outside function. So that means 2, and then x plus 3 to the power of 1 less than 2, which is power of 1. Let's make this a little bit more obvious. So there is an outside function here as well. But as you can see, the inside function, yes, it is a function on its own, but the rate of change will be just 1 because derivative of x plus 3 is 1. So now we have to clean up this expression. So we'll have u squared plus 3 to the power of 3. And then we have plus. And here we go, 2u squared times 3, 6u squared. And then u squared plus 3 to the power of 2. And then in the other brackets, we have 2x plus 3. So if you want to simplify, we can definitely do that. So we have u squared plus 3 in here, a common factor, power of 2. So we can take that out. So u squared plus 3 to the power of 2. And in brackets, we'll have a u squared plus 3 to the power of 1 left from this power of 3 here. And 6u squared, which will be the factor that is left from here. Close the brackets. And here we go, we have 2x plus 6 here. We can expand this. So we can start by bringing in the the function u, which is the function x plus 3 squared. So we'll have in here x plus 3 squared plus 3 to the power of 2, multiplied by, so you have u squared and 6u squared, 7u squared, so 7 x plus 3 squared, again, squared, and then plus 3. And this entire thing has to stay in brackets. So, okay, remember now, so 7u squared, so 7u squared, and then plus 3, so plus 3. And now we're multiplying this by 2x plus 6. As you can see here, we have only x in the derivative, so we can simplify these two powers, so you can bring them together as a power of 4, or we can start substituting x by negative 2. So if we substituted x by negative 2, let's see what we get. We have brackets, negative 2 plus 3 squared, and then plus 3, all of it to the power of 2. We'll have a 7. We have negative 2 plus 3, here brought to the power of 2 to the power of 2, that's to the power of 4. So we're combining the powers in the meantime and substituting x by -2, and then plus 3. And then down here we have 2 times -2, and then plus 6. All right, so let's see at all the 2's that we have substituted. So these 2 -2's in here. So these are all the x values substituted. Now we have to simplify. So it's kind of nice that we have -2 and 3. So that will make a 1 in here to the power of 2 plus 3. Next we have a 7 times 1 to the power of 4 plus 3. And lastly we have -4 plus 6. So that will mean we have a 4. 7 plus 3, 10. -4 plus 6 is 2. And 40 times 2 equals 80, which means the derivative of this function in terms of x, or function y in terms of x, measured at x equals -2, would be equal to 80. So in a similar way, we can work with the last equation. I'm going to continue with a new video for it because this became a little bit too long. Bye for now, and thank you for learning with me. Stay tuned.